All right, today we're going to take a look at our last lesson on interest, which is compound interest. Yesterday we basically built up to compound interest. It's just we used simple interest equations to do it, and we found out that it was long and tedious. So what we're going to do today is I'm just going to make an observation by taking a look at yesterday's example, or sorry, I should say yesterday's practice problem. So what you should have saw in the practice problem was that you were investing $200 and you were basically putting it in at 36% a year, but you were taking it out and putting it back in every month for 2 years. And what you should have noticed is that your R value, your interest rate per year, was 36%, and your time in years was 1/12, which is 1 month. 1 month is 1/12 of a year. When you take the 1 plus RT part, you get 0.03. So in order to find out how much you'd have after 1 month, you would take 200, multiply it by 1.03, and you'd have $206. Then you'd then take the $206, multiply it by 1.03, and after 2 months, you'd have $212.18. And then you'd multiply that number by 1.03, and you'd multiply that number by 1.03, and that number by 1.03, and you do that 24 times in total, and your final number would be $406.56. Well, what I want to point out is that there is actually an operation that does that much faster that we are familiar with. Now, instead of taking 200 and multiplying it by 1.03 24 times, an easier way to do that is to just say, let's multiply 200 by 1.03 to the exponent 24. Now, if you came up with that on your own, fantastic. That's actually one of the reasons that we built up to it using the method we did yesterday. And what we can notice is that we can solve basically any compound interest equation using something very, very similar to that. The only difference is, and I look at that equation, 200 times 1.03 to the exponent 24, I don't see the annual interest rate of 36%, and I don't see the total time of 2 years. The numbers I see are 1.03 and 24. So the 1 we know is 1 plus RT. Well, R times T has been replaced with 0.03, which is our interest rate not per year now, but it happens to be the interest rate per month. So 36% a year divided by 12 is 3% a month. And 24 is no longer our number of years, it's our number of months. So in this case, 24 months. So now we change our variables just a little wee bit, and we come up with this equation, a equals p times 1 plus I to the exponent n. Now the good thing is the a and the p are the exact same variables they were with simple interest. A is still the amount that we have at the end, the accumulated amount, and p is still the principal, the amount that we have at the beginning. The only thing that's changed is instead of having an R and T, R being interest rate per year and T being time in years, we now have I, a lowercase I, which is the interest rate per compound period, and N, which is the number of compound periods. So a compound period could be months, it could be weeks, it could be days, it could be pretty much anything you want it to be. So let's use the equation, this new equation, to solve the question that we did yesterday in the practice problem, but much, much, much faster. So the question was, we're investing $200 for 2 years at 36% a year, and we're going to compound it every month. So it's equivalent of taking the money out and putting it back in every month. We're just going to start calling that compounding. So according to our new equation, we're looking for A. We're told that the principal is $200. The I is the interest rate per compound period, so 36% per year divided by 12 to get 3% per month, or 0.03. And N is the number of compound periods, which is 2 years times 12, or 24 months. So you'll notice that the interest rate was the annual or the yearly divided by 12, which is the number of compounds in a year, and the N was the years times 12, which is the number of compounds per year. So interest rate got divided by 12, the number of years got multiplied by 12. So now we just take A equals P times 1 plus I to the N, and that's 200 1.03 to the 24. And when I punch this into my calculator, remember BEDMAS says we have to do the exponent before the multiplication. So 1.03 to the exponent 24. And that gives us a number a little bit over 2. And now we multiply that by 200, and we get $406 and what rounds to 56 cents. Now, if we compare that to what we got yesterday, did we actually write down? Yeah, there we are, $406.56. And I would say that that is a heck of a lot faster than doing it one compound period at a time. And that was only 24 compound periods. If we were compounding weekly for 20 years, there'd be over 1,000 compound periods. Whereas this equation wouldn't be any bigger. It would just have different numbers in it, but it would still be the same length to punch it into our calculator. Now, a little note down here that I wanted to make certain that we understand is that be careful when you're rounding off, especially with this number right here. Now, in many of our equations, I is going to work out to a nice number that we don't need to round, which is good. A small difference in I can create a big difference in the answer because it's often to a fairly large exponent. So changing that number even slightly. So for instance, if I had put in 200 times 1.04 to the exponent 24, so just made that R value or that I value just a little wee bit bigger, that would have given me over $512. So my answer would have been off by more than $100 out of around 400. That's 25% error. That's pretty big. So try not to round off I more than you have to. If you can have the exact value in your calculator, that's even better. If not, try and keep a few decimal places. So let's try an example. Greg invests $3,000 for 20 years at 26% a year, compounded weekly. How much will he have after 20 years? Now again, 26% is a pretty high interest rate for an investment. In fact, it's possible, but astronomically high and usually not something that would be consistent. That would be if you invest in like a really big up and coming company that happened to do really well. But that's still a really, really good investment. Not something you'd get for 20 years. But let's just use that because it's a nice number, or at least you'll see why it's a nice number in a moment. So we're told that Greg invests $3,000. So that's a principal. 20 years is time. Now, before I write that down, I don't want to write down t equals 20 years because this is going to be a compound problem. And in fact, it's compounded weekly. So it's not t we're writing down, it's n, the number of compound periods. And the number of compound periods is 20 years at 52 compounds a year, since there are 52 weeks in a year. So 20 times 52 is 1,040. And we're told 26% a year, but again, we're not looking for R anymore. R was simple interest. That's always percentage per year. Now we're looking for percentage per week. So that's going to be our lowercase I. And it's 26% a year divided by the number of compounds in a year, which is 52. And 26% divided by 52 is 0.5% or 0.005. Okay, so notice that even though 26 may not seem like a great number, when we divided it by 52, it worked out to be exactly 0.005. So that was why I chose it the way I did. And we want to know how much we're going to have. That's going to be our A. So now that we've got that, A equals P times 1 plus I to the exponent n, which is 3,000 times 1.005 to the exponent 1,040. Now, before you even punch that into your calculator, how much do you think the answer is going to be? Like, Greg invested $3,000 for 20 years. Is he going to have like $10,000 or $50,000 or $100,000 or $1 million? Like, just take a guess. And then when you've got your guess, let's figure out how much it actually will be. I think most people find it a little surprising. So again, remember that we want to do the exponent before the multiplication. If not, you'll get a ridiculous answer. In fact, I think it'll break your calculator. So 1.005 to the exponent 1040, and then multiply that by 3000. And our answer is $536,816.04. Now, I kept exact values in my calculator, which actually I think most people would because we didn't have to round off anything to this point. But again, don't be too freaked out if my answer is a little bit different than yours because of rounding error. Now, if you got like $7,000, then that's not a rounding error. That's just a mistake. But if you got $537,100, that's probably a rounding error. Before we go to question 2, I'm going to point out that there are a couple of compound periods that are not obvious. Monthly is 12 times a year, weekly is 52 times a year, daily is 365 times a year. But we also have semi-annually and quarterly. Now, semi-annual just means twice a year. Semi is like half a circle, like a semicircle is half a circle. So semi-annual is half a year. And if you compound every half a year, that's twice a year. Quarterly is basically break it into 4 pieces. So there's 4 compounds per year, basically 1 per season. So for question 2, Chantel borrows $400 for 8 years at 16% a year compounded quarterly. Now this time 16% interest is actually very reasonable. Unfortunately, when you borrow money, you tend to pay a lot higher interest rate than when you lend money. So 16% a year is actually less than a credit card, but it's still a hefty amount to have to pay. So let's see how much Chantel is going to have to pay after 8 years. And if you want to make an estimate on how much she's going to owe, do that now. Do you think she's going to owe like $500 or $700 or $1,000 or $2,000? Just take a guess, and then let's see what happens due to compounding. So she borrows $400, which means the starting amount, principal, is 400. Now again, we want to say 8 years and 16% a year, but I'm going to look first to find out that it's compounded quarterly, because we're not looking for R and T anymore. We're looking for I and N. So 8 years is really related to our compound period. There's 8 years, but at 4 times a year. So there'll be 32 compounds. And the interest rate is 16% a year, but it's divided by 4 because we need interest rate per quarter. And that's 4%, which is 0.04. And how much we'll have at the end, that's our question mark. So A equals P times 1 plus I to the exponent N. That's 400 times 1.04 to the exponent 32. BEDMAS says do that exponent first. So 1.04 to the exponent 32 gives us a number about 3.5, and multiply that by 400. And it looks like Chantel is going to owe $1,403.22. Okay, so she borrowed $400 for 8 years and had to pay back $1,400. I hope she enjoyed whatever she bought with that $400 because it ended up costing her quite a bit down the road. And by the way, this is the kind of thing that happens is people think about this. If 8 years ago you bought a $400 television, that would be like a 32-inch LCD. Actually, it was probably, yeah, it would have been an LCD. So you would have paid $400 for a 32-inch LCD television, and now you'd owe, 8 years later, $1,403 for that TV, which you could go out and buy for like $250, maybe. So, I mean, think about how much interest you're building when you buy something on a credit card. It can be kind of crazy. And our next unit after, I shouldn't say that, 2 units from now, we're going to talk a little bit more about borrowing money and the effects of compound interest and how much money you're going to owe if you don't pay things off promptly. Okay, so how much interest does how much interest does she end up paying after 8 years? Now, again, this is one of our equations, but it's almost intuitive. If she borrowed 400 and she paid back 1403, then we just subtract 400 from that, which is basically the equation A equals P plus I. So 1403.22 equals 400 plus I. Subtract 400 from both sides. And usually, again, I like to write the variable on the left. So, oops, one too many zeros there. Interest equals $1,003.22. So she paid $1,000 for the privilege of borrowing $400. That's how interest works. All right, from there, I'm going to let you try some practice problems. A couple of them, questions 1 and 4, I believe, are ones where you fill in tables. It's just to make sure that you're using the correct I and N values, trying to get away from the R and T's that we use with simple interest. And then questions 2, 3, and 5 are going to be actually calculating things based on that. So for the answers, you'll notice that I did give you the exact values for 1 and 4 because I want to make sure you're filling in those tables correctly, exactly correctly. And then the others are approximate answers that are giving you pretty close to the correct answer, but you have to get the exact value. If you need help, let me know. Otherwise, good luck.